Okay, so I think we can. So yeah, welcome everybody for our next summer N3AS seminar. And today we have André who will be talking about Lattice QCD and mainly its applications to nuclear physics and possibly also nuclear astrophysics. So please, André, go ahead.
Okay, thank you very much. Thank you guys for having me. I always enjoy if you want to interrupt me during my talk. That's always more fun than waiting till the end. And I took the 25+5 seriously, though I'm not always good at staying in time, but maybe I'll go a little fast, but the intent being to leave as much time for questions as possible. And of course, in 25 minutes, what can I tell you about lattice QCD and nuclear physics? I can only flash some results. I can't really go into any detail. So let me show you my propaganda slide. My claim is lattice QCD is potentially, I'll say, I won't say is, I'll say potentially useful for a huge range of physics. Why is the matter or universe composed of matter, not antimatter? Does dark matter interact with matter beyond gravitationally? What is the neutrino nucleus scattering cross section? What is the property and composition of dense nuclear matter? Ones you might have an easier time believing are, can we say something about the neutron lifetime or the properties of the proton, the parton distribution functions of the proton? So how does this, what's the claim this will work? Of course, we can't use lattice QCD to compute nearly any of these quantities directly or quantities that feed into those processes directly. But in each of those examples, there's maybe some one or two key pieces of information that are either very challenging or impossible to measure experimentally alone. And this is where lattice QCD can help. And in order to succeed for anything other than just the proton, this will require some coordinated effort, or even with the proton. I'm not going to talk about it today, but neutron beta decay is another example. Even with single nucleon quantities, this will require some coordinated effort between lattice QCD, effective field theory, and in many cases, people know how to compute properties of nuclei, so many-body nuclear physics. And here, I'll point you to a review article I was involved in with Christian Drischler and a few others, where we tried to comment on the challenges and prospects for sort of making this connection. And here's just a cartoon, essentially, of saying what I just said. Here it's some small neutron number or proton number. We know we're described protons and neutrons in terms of quarks and gluons, and also the deuteron. And maybe we can possibly compute, a few neutron systems, or we can compute light atomic nuclei. And then the goal would be to match these onto some effective field theory description of the same process. So match the S matrix elements and essentially determine the low energy constants of the effective field theory you can't access experimentally, or determine the ones you can to try to validate the lattice QCD approach. So like reproduce the deuteron binding energy, for example. And then once you've pinned down those few couplings you don't know, you can use them to make calculations of more interesting problems. And then this also lets you propagate the theoretical uncertainty directly from QCD into these bigger nuclear systems. And then once you do that, you can couple on to some many-body effective field theory. And once again, for many-body theory, doesn't necessarily have to be an effective field theory, and propagate that theoretical uncertainty into even larger nuclei. And I'll just pick one example of the many where maybe we can say something, and that is, as you all know very well, we've entered this new multi-messenger era of nuclear astrophysics, and the ability to measure properties of neutron stars is making it very exciting, for example, to try to pin down the equation of state. And as you're all very familiar with, if you have a neutron star that's two solar masses, it's simultaneously difficult to imagine the core density isn't such that hyperons do play an important role. And at the same time, once you add hyperons into the mix, how do you keep the equation of state from softening too much so that the star collapses? And the relevant quantities here would be, the first thing you might access with lattice QCD is hyperon nucleon scattering. And because the hyperons decay so quickly, we don't have very much experimental data on these scattering cross sections. And so with Lattice QCD, you can pin down the low energy scattering cross sections, not at the densities you're interested in, but at least you would be able to do it in a range of validity where you could, use your finite density theory and go to low density and quantify and validate what's going on, and then try to propagate that information to a higher density system. And the 3 neutron interaction plays an important role in helping to stabilize a neutron star. And so probably, if once you add hyperons into the mix, the 3 body hyperon nucleon interactions are probably also very important to stabilize the star so you don't soften the equation of state too much. And again, this is something you can start to address with hypernuclei experiments, like looking at spectroscopy of light helium with some lambda particles in it. But with Lattice QCD, you can come in and pin down like the 3 body force and some other things that maybe you can't get experimentally so well. Okay, so now I have a rapid introduction to Lattice QCD. So Lattice QCD is just the Euclidean. It's a Euclidean version of QCD. So here, everything we do in theoretical physics is we calculate correlation functions, create some state at time 0, annihilate it at time t. And I can represent this with a path integral. As you know, we don't know how to solve this path integral if it's a non-perturbative system, but the quarks are, quadratic, and the Lagrangian of QCD is quadratic in the quark field, so you can do that integral exactly, and you end up with some determinant. We still don't know how to solve the theory, of course, but then what we can do is we can stick the entire theory into a finite space-time volume. We can discretize it. Usually we just use a regular rectangular grid. Of course, we still can't do the integral because there's too many degrees of freedom. So even if you put this into a 32 cube by 64 lattice, there's, I don't remember, but there's like 10 to the 20 states or something. There's no way to do the integral. You put the gluons on the links, the quarks on the sites, and then to have any hope, what you do is you go to Euclidean space. So this e to the I action, e to the is, turns into e to the minus s in Euclidean space. You notice also the I disappears from the derivative. And then the great thing is if you're at finite chemical potential, this determinant and the action are both real numbers. And so then what you can do is you can use this quantity, that it's quark determinant times the exponential of the action, as a measure of probability with which to sample gluon configurations. And so then what we do is we set up a Markov Monte Carlo chain, and we generate snapshots of the glue. And the idea is to find values of the gluon field configuration that make S as small as possible, maximizing the probability. And then this correlation function has an exact answer stochastically. This path integral just turns into a mean of the correlation function evaluated on each of the background configurations. And then there's some error in the correlation function that improves with the square root of the number of measurements. So just to point out, I think, especially if you're not in the field, a lot of people think of Lattice QCD as some sort of black box, which you can use to just calculate any process you want. And of course, this is very non-true. It takes a lot of ingenuity to try to come up with good ways, both computational ingenuity, but also physics ingenuity, to try to design new ways to do the calculations to get to the physics we want faster. And then there's a very highly non-trivial numerical analysis step, which takes you from the correlation function you compute to the actual observable quantity you care about. So maybe by the time I'm retiring, like next year, we'll have some iPhone app where you can calculate the 2 nucleon scattering cross section on your iPhone. All right, so then you do this whole rigmarole, and what do? Well, it's a discretized theory, but we want to describe QCD, which means we have to take the continuum limit. And the minimum number of lattice spacing you need to properly quantify the uncertainties you go to the continuum limit is at least 3, right? Because if you have some theoretical prediction for the discretization error, like say it goes like a squared, you better have at least 3 points to ascertain whether your extrapolation to the continuum limit is well described by just the linear a squared correction, or do you need some higher order correction to properly characterize the approach to the continuum limit? And this is in essence why Lattice QCD is so expensive, because you can get some of these powers, but basically the full computational cost to take the continuum limit scales like, in the best case scenario, scales like 1/6 power of the lattice spacing. And it gets even worse as you get close to the continuum limit for reasons we could talk about. So you get 4 of these powers just because you have a 4-dimensional theory, and then you get another power because when you go to the continuum limit, your condition number, the ratio of the largest to the smallest eigenvalue, also has some scaling in the lattice spacing. And then you also have some autocorrelation time, and so it's an approximate 1/8. And then, of course, you want to take the infinite volume limit. The universes we typically simulate are just 2 to 4 Fermi across. They're not much bigger than the size of a proton. And then what's really killer for nuclear physics is as you go to the physical pion mass, you have an exponentially bad signal to noise problem, which I probably won't say anything more about. So let me just walk you through some very basic math. I have the same 2-point correlation function that we were talking about before. Creation operator at time 0, annihilation operator at time t. And for the simplest things, what we do is we compute what we call a mixed time momentum correlation function. So I only do a Fourier transform in the spatial directions. And in this particular one, I'm only doing it out the sinc side. So I have some creation operator, a local creation operator, a local annihilation operator, but then I Fourier transform that overall space to project to a state of definite momentum. And yes, the most common boundary conditions we use are periodic boundary conditions in space and time, except for the fermions, which have an anti-periodic boundary condition in time, such that we can interpret the finite time extent as a finite temperature. So this is important for people doing finite temperature lattice QCD. But also, if we the simplest way to understand the correlation function is if we give the fermions anti-periodic boundary conditions in time. And I'm completely ignoring the boundary conditions in this formula here, as you can probably tell. So now what I do is I've lost my momentum somehow here, going from line 1 to 2, but we can ignore that. What I'm going to do is, oh no, I haven't read my slide in more than a few hours, so I forgot. Look, I'm still summing over x, and I'm just putting momentum to 0. So I'm going to focus on the 0 momentum correlation function. All I had to do is read my slide, and then I could tell you what I'm doing. And then what are we going to do? We're going to time evolve the operator at t back to the origin. And because we're in Euclidean space, you notice there's no I in front of the Hamiltonian operator. Then, as theorists, what do? We multiply by 1 or we add 0. That's the only tricks we know how to do. So in this case, we're going to multiply by 1 in the form of the identity. I'm going to insert that identity between this creation operator and the Hamiltonian. We'll define the vacuum to have 0 energy. And so then the Hamiltonian acts on this state n, pulling down the nth energy level. And then everything else is just a time independent constant. So we usually call these overlap factors. You'll hear us call that, or sometimes we get a little sloppy and we call them wave functions. So these are interpolating fields to create a state out of the vacuum. And again, because this is QCD, it's a non-perturbative theory. We don't know how to write down the exact interpolating field to create only the proton. The only thing we can do is write an interpolating operator that has quantum numbers of the proton. And then it will excite every state in the vacuum that has the same quantum numbers of the proton, which is why I have a sum over states here. And this makes life difficult, but it is what it is. And so now what do I have? I have this sum of energies all at 0 momentum. And so then the 2-point correlation function is described by a sum of exponentials. Doesn't seem so bad, except the problem is, fitting exponentials to noisy data is an ill-conditioned problem. And that's what we have to do to extract those energies. And so if you wait for a long enough time, then what you, of course, well, first of all, this expression doesn't depend on long time or not time, but I can rewrite this correlation function as the ground state overlap factor times the exponential of the ground state energy times 1 plus a sum. Here are our ratios of the excited state to ground state overlap factor. And now these ENs are gaps to any energy that's not the excited or the ground state. And so if you wait to a long time, all these excited states will exponentially decay away, letting your correlation function be saturated by the ground state. And one thing we do to observe if this has happened is we construct what we call an effective mass. So for what I was showing you before, this effective mass is simply the log of the ratio of the correlator at some displaced time. Here I've just chosen displaced by 1 unit. And if you just stick this formula into this this logarithmic function, of course, what you get in the long time limit is you just get the energy plus a sum of small corrections, which decay exponentially. And this is what we see with the pion. You get this very beautiful, we call this a plateau. So this means by eye, I can observe that the energy of the pion, the mass of the pion is approximately 0.133, say. And I can do an actual fit. And here, this blue line is a fit, and it's a one state fit to the correlation function itself, and I extract a very precise pion energy. No problem. Okay, but then if you want to do baryons, this is where life becomes difficult. Here I'm showing you results from an omega baryon mass. And what this little key here means is that it's a lattice spacing of about 0.09 Fermi, and the pion mass is about 135 MeV. So I'm sitting at the physical pion mass, but not at the continuum limit, of course. And even for the omega baryon, what you see is a function of time. The effective mass, the noise of the data grows as a function of time. And this is a very key issue as to why it's challenging to do nuclear physics applications with Lattice QCD. Because how do you actually identify the ground state energy? If I were to wait till a long time and do a 1 exponential fit, I could get an answer here that's reasonably precise, or I could go out later in time and get an answer that's less precise. What you can see is getting a precise, robust, and stable answer is challenging if I just try to do this with simple fitting techniques. And in fact, other problems that show up are the data are highly correlated. And so you could be unfortunate and you could be sitting on a correlated fluctuation, because as the noise grows, these distributions of the correlation function they're not nice Gaussians anymore, but they're often log normal distributions, or they're heavy tailed, or the mean is a very small number compared to the width of the distribution. And so you can run into all sorts of trouble. And so what we do is we try to come up with very exhaustive, extensive analysis techniques to find a robust and stable answer. And that's what I'm just plotting here. I'm doing a bunch of, this means a 1 exponential fit, NS of 1, 2 exponential fit, 3, and so on. And I fit it as a function of T min. And then what you can do is look for some stability in the extraction of the ground state energy. And in this particular case, I just chose this as an answer to guide the eye, but you could come up with some way to weight all of these answers and build in a complete systematic uncertainty of your ability to determine the ground state. All right, so that's Lattice QCD. And now I'm going to jump into, I'm just going to show you some selective highlights of things that we've accomplished recently. Nuclear and axial coupling, axial form factor, the pi minus to pi plus matrix element, which is would show up from some prospective 4-quark 2-electron operator contributing to double beta decay, and something that's more for fun than use, exploring the sensitivity of Big Bang nucleosynthesis to isospin breaking, which is something I know many people here have thought about a lot more than me. Okay, nuclear and axial charge. So here's a little cartoon picture. You have a neutron. At some point, the weak interaction causes a spontaneous emission of electron and a neutrino, and it turns in a down quark to an up quark, and then we get a proton coming out. And this is interesting, or it got even more interesting. It was interesting at first because the community, the lattice community, was using GA as a benchmark quantity to try to convince the rest of the nuclear physics community that, hey, look, we know what we're doing with Lattice QCD, you should believe everything else we're doing. But then it turned out there's huge systematic uncertainties in calculating GA. So it took something like 10 years longer than the community expected to come up with a stable answer for GA. And in the meantime, there's this nice discrepancy between the beam and the bottle measurements of the neutron lifetime uh, with some 4 sigma tension, as you probably know. And in this expression, every quantity here, or most of the quantities you can measure experimentally, including you can measure, of course, GA experimentally. Uh, but GA is something you can't predict from theory, whereas like VUD, of course, you have to determine this experimentally. The Fermi constant, you have to determine experimentally. The electron mass, you have to determine experimentally. The lifetime, of course. But sort of the phase space factor and the radiative corrections are things you can compute theoretically. And also the nucleon axial coupling is something you can compute theoretically. But of course, you need a big computer. And as it so happens, GPUs were disruptive for Lattice QCD because essentially the thing that takes more time than anything else in Lattice QCD calculations up until recently is solving the inverse Dirac operator or a quark propagator. And what it is basically, it's a solution to this Green's function. And here this Dirac operator is a large sparse matrix. You want to find an inverse of the matrix. That's basically linear algebra. Use a conjugate gradient algorithm or something. And GPUs are really good at this. And so this aspect of the calculation got factors of 10 to 100 speed up by the introduction of GPUs plus some other algorithmic advances. And then a few years ago now, with a few other colleagues, what we did is we were able to compute the axial coupling of the nucleon. And essentially what we did is we weren't in the community of people doing this calculation. So when we came at it, we just reinvented the wheel, as it turns out, but we came up with a different approach that was not common. Turns out it was invented back in the 80s by some Italians, Martinelli and company. But we thought we'd uncovered some grand new way to do all sorts of calculations. And in the process of doing the calculation, we learned, okay, actually the idea's been around for a while. But we were able to do this very nice calculation where we actually, for the first time, we were able to get a percent level estimate or determination of the axial coupling of the nucleon. And because we're using this alternative technique, the community had estimated, in 2020, you might get a 2% result, but back in 2018, we got this 1% result. So we were really excited and we managed to convince some referees that they should publish it in Nature, which was of course exciting, even though often we associate Nature articles as vacuous, contentless articles that are just used to show off the field. And of course, we disagree that our result was not vacuous, but that's a sort of irrelevant. And at the time, experiment was 6 more times precise than what we could achieve from Lattice QCD. So we're not trying to compete with the precision with which you can determine the axial coupling. And after that, new experiments came out per KO3, which are now a factor of 20 times more precise than we were able to get with Lattice QCD. And essentially, there's no hope Lattice QCD will be able to match this experiment. But what gets interesting is we can start asking questions about, well, what are corrections to GA from strong isospin breaking or QED? And that's relevant for if we want to compare this number to the measured value of GA. The measured value of GA is possibly polluted by right-handed currents from beyond the standard model. And also it has QED corrections. And so if we want to compare the measurement to the pure QCD value, then we have to have a way of rigorously determining those extra corrections. Basically, you need big computing, you need really good code, you have to have a community that shares resources. So the Milk collaboration gave us their configurations and a new technique, and that's how we leapfrogged ahead of others. And then what's exciting now is this was back in 2018 and the new computers are ridiculously faster. So we haven't published an update yet, but this is just one way to show you how much faster. So this green point here on the left plot was like 90% of the cost of our entire calculation. Like all these points combined added up to just a fraction of the cost of this one green point. And you can see this green point, the uncertainty is so large, it's not impacting the extrapolation, in this case as a function of the biomass down to the physical point. It's just there to guide the eye and feel like we did something successful. We had 3 sources per configuration, so 3,000 different sources. And this took a whole year on the fastest supercomputer at the time. And then we got access to the early supercomputers. And again, this is back in 2018, 2019. I had a colleague at Livermore who has access to the Sierra computer. And in 2.5 weekends on Sierra, we were able to take these 3 sources up to 16 and do a much better job. And now you can see our result at the physical biomass. These results are now precise enough to influence the fit. And fortunately, they're not tugging the number to be inconsistent with what we had before. So we have this updated result that's not published. It's just in our proceedings. And we're sitting on results where we can probably get GA down to 0.5%. We're not proceeding yet because turns out the QED corrections are larger than the community thought. So we have to address QED corrections as well. Okay, now a couple very short comments on the nucleon axial form factor. So we know the Dune experiment is designed to resurrect the dinosaurs between Fermilab and South Dakota. And in order to do so, they have to measure the properties of neutrinos associated with flavor oscillations. And as you know, this is a very challenging theoretical problem to try to predict the neutrino argon cross-section. And then, of course, there's also the Hyper-K experiment that's also going to measure similar properties of the neutrino oscillation matrix. And here on the right, what do we have? We have a plot of the unoscillated neutrino nucleus cross-section as a function of energy coming out of the Monte Carlo generators. And what you see in different lines here are contributions from different contributions to the cross-section. So we have the charged current quasi-elastic like cross-section. There's the resonance cross-section, this orange guy down here. There's the deep and elastic contribution. And then the black gives the total contribution. And so what you can see is over the energy range, this is a very complicated problem. There's no single theory that you will be able, with a robust theoretical estimate or uncertainty that you'll be able to use to describe the entire process. So you have to try to figure out how to glue together theories in different regions of validity to describe the total cross-section. What's interesting is in the event generators, is there a preference from the bottle? Sorry, I'm just looking at the chat. Is there a preference for the bottle beam neutron lifetime from I'll show you a slide.
André, we can save that for the end.
Yeah, I'll show you a slide when we're done.
Okay, thanks.
I laugh because of how irrelevant we are so far. But okay, coming back to the axial form factor, we have a 50. So in the event generators, the pion production model that is used is the original model from 50 years ago by Feynman, Kisslinger, and Ravindal. And in their paper, they describe the model as naive and obviously wrong, but it's still the model that's used in all these event generators. And so one, I think it's natural to worry or wonder if you could improve the theoretical description of pion production, would that enable you to make a better, or really what I mean by better is a prediction of the cross-section that is less sensitive to modeling uncertainty? Of course, the answer is yes, but it's really hard to improve the model, especially because there's no experimental path forward to improve the basic neutrino nucleus cross-sections that you need to feed into these event generators. And that's exactly where Lattice QCD can come in. We can calculate the quasi-elastic form factor. We can calculate the resonant inelastic nucleon structure. Of course, that's very related to the pion production mechanism. And we can build up and start calculating 2 nucleon axial corrections. And so these can all be fed into the theoretical models that describe the nucleus. And piece by piece, from the simplest to slightly more complicated, we can sort of replace what's been done extracting this information from experiment or phenomenology with a rigorous first principles prediction. And you might say, well, does that matter? Is it helpful? So here's a picture from a recent review with Aaron Meyer and Caleb Wilkinson. So Caleb Wilkinson is a member of the T2K and Dune collaborations. And what we did is we looked at the Lattice QCD results for the axial form factor of the nucleon. And this is what we have in the upper left. So the bands, what are the bands? The bands are from the what's called the enemy. I call them the enemy because it's one of my competitors. We have a nice friendly uh, competition, and he named his collaboration such that I can call him the enemy. Of course, he didn't really do it for me, but it's fun. And then our QCD is the Regensburg QCD. These two groups have done a full continuum extrapolation and extrapolation of the physical pion mass. So they have, the band represents their best estimate of the full theoretical uncertainty from the data set, the Lattice QCD numerical data set they have. And then the results shown with dots and hashes, or the error bars, those are results from single ensembles at or near the physical pion mass. And the point to take away from this is Lattice QCD results are pretty much lining up to be consistent with these extrapolated bands from the other group. And you'll notice there's noticeable tension from the parameterization of the form factor you get looking at neutrino deuterium cross-section measurements, and then using a model of the deuteron to tease out the single nucleon piece. So this is rather significant tension. And then if you take that and you stick it back in to predict the full neutrino nucleus cross section, what you see, of course, it's proportional to the square of the amplitude. And so when you put that change in, what you observe is in fact the single nucleon cross section is observed to have about a 30% enhancement compared to what you would predict from just taking information from experimental results and some phenomenology to extract a single nucleon. So I'd say, in fact, this is very relevant because if you increase the single nucleon cross section, of course, you're going to increase the total neutrino nucleus cross section. And here what we did with Calum is we ran these through the event generators for the near and the far detector. So we didn't do what you would really do, which is change other parameters in the model to describe this change in physics, but we simply swapped out the single nucleon axial form factor and just to get an observation of what would happen. And what you can see is this blue line is the nominal Gini result. And then the pink line above it is the result from swapping out our form factor from the preliminary Lattice QCD result. And then in the near and the far detector, of course, this bottom plot shows the ratio of sticking in the Lattice QCD form factor to nominal. And the shape is energy dependent, and it's not the same in the near and the far detector. And so this has the potential to interfere with your ability to extract the neutrino oscillation parameters you care about. Okay. Within a couple of years, these Lattice QCD results should really be pinned down, and Lattice QCD can deliver a kind of a final result. And I have no reason to believe it's going to move away from these bands here. But you remember there's some long history of Lattice QCD not getting GA right. And so you want to make sure, you really want to make sure we're going to get FA of Q squared right as well. And we're not somehow missing some systematic. The systematic uncertainties that polluted GA also mess with the axial form factor, but now the entire community is very aware of these systematic uncertainties. So we're pretty confident it's pinned down, but wait a couple of years, 1 to 2 years, and this will be sort of a settled result. And then the frontier is looking at like delta resonance or pion production off the nucleon. Okay, now I'm going to jump gears to double beta decay. Unless there's questions on that stuff, just watch the chat if anybody wants to speak up. So double beta decay. This is exciting, of course, because if you observe neutrinoless double beta decay, you get a Nobel Prize. And what's interesting about it is, this is a problem that we think we understand very well, but it's based on essentially predicting the long range component from the light Majorana neutrino mechanism. But there's all sorts of models that are equally plausible that can give you sort of short distance corrections. So where perhaps this is a heavy neutrino, and if heavy, it just has to be heavy compared to QCD scales. This is going to look like a local 4-quark operator in terms of embedding this in a 2-nucleon system. And essentially, this is not something you can measure experimentally. So the only hope of ascertaining the importance of such contributions is with a tool like Lattice QCD coupled with effective field theory. And of course, it will be in terms of some parameters you don't know, because the BSM physics will give rise to some Wilson coefficients that accompany the operator. And so what you would do is you'd build an effective field theory description that parameterized this potential new physics in terms of, at the low energy QCD scale, all the relevant operators that would appear. You can compute those matrix elements in a double beta decay system on Lattice QCD, and then you could predict as a function of the, in this case, there's 5 operators that appear at this order, what would be the double beta decay rate if it were modified by the presence of these operators. You can also use Lattice QCD to tease out the 2 nucleon corrections to GA. So if you have a single axial current in a 2 nucleon system, there's this short distance in the effective field theory language CD coefficient that describes the axial coupling of 2 nucleons to an axial current. And this is also relevant for tritium binding energy and other things, dark matter detection. And so with Lattice QCD, the community is doing pretty good job pinning this down. And so this would be more of like a confirmation probably by the time Lattice QCD gets around to computing it, but you can really come in and you can calculate these short distance effects directly with QCD. Now, if we return to the short range correction, something you can't measure experimentally, then what do we have? If we go to extremely low energy, this matrix element just looks like a pi minus to pi plus transition. And at least in what's called the Weinberg power counting of 2 nucleon systems, this gives you the leading order correction, which scales like 1 over q squared. Whereas the short distance 2 nucleon operator scales like q to the 0. So this has an enhancement compared to the short distance operator. That's only strictly true in what's called the Weinberg power counting, as Vincenzo, who I saw here, can tell you all about. If you switch to what many people believe is a more realistic power counting, you actually have to promote this contribution to be the same order as this pion exchange contribution. Otherwise, you can't properly renormalize the effective field theory. But what we can do on the lattice is it's very easy to compute pions. And so we just stick in these operators. We calculated the pi minus to pi plus transition matrix element. Once you have those, it's easy to write down the form of the 2 nucleon, the 2 neutron or 2 proton potential arising from such matrix elements. And so you could feed those into some effective field theory to describe the 2 nucleon system. And then once you pin down those potentials, you could feed them into a many body or an ab initio calculation, say, which you could then match on this many body system and actually calculate the nuclear decay, the nuclear matrix element. This is what the Lattice QCD result looks like for these 5 matrix elements. You'll notice one of them is very small compared to the others, and that's understood. It has a chiral suppression that comes proportional to an m pi squared, where the rest don't, or an m pi squared suppression compared to what the rest of the operators have. And so this was fun because it was a case where, for whatever reason, nobody had ever computed this quantity before. And so once we sniffed that you could do it, we were able to not only do the first calculation, but we were able to do a complete calculation, meaning a continuum extrapolation and an extrapolation of the physical pion mass. So for example, the different dashed lines are results from different lattice spacings. And then the band is the result of extrapolating those lattice spacing results to the continuum limit. And so then, for example, we could give these matrix elements to Ken, Wick, or anybody else who's interested. We've basically computed the strength of these OI coefficients, and then this is the form of the potential once you have these operators, and then I can compute the 2 neutron to 2 proton matrix element. Okay, so then the last thing I want to talk about, so I'm taking longer than I want, Big Bang nucleosynthesis. Since I assume most of you understand this physics very well, I'll just kind of rush through this. In the early universe, we have a hot compressed gas of neutrons and protons, about a second after the Big Bang. The reaction rate of protons and neutrons goes roughly equal direction into converting into deuterium and a photon. We hit the magic time of about 3 minutes after the Big Bang when we cool off, so that this reaction rate predominantly goes one way and just forms deuterium. And once you form deuterium, you rapidly form helium-4. And then at roughly 15 minutes, all free neutrons are going to decay out of the system. And that we know is just described by some complex reaction rate of light nuclei. And in this study, I'm just mostly going to focus on these very light nuclear reactions occurring down here. And then, as you know, there's this nice consistency. If you were to ask from measured or observed abundances of helium, deuterium, and hydrogen in the universe, you would predict. So this whole Big Bang reaction network, once you know all the reaction rates, just depends on this asymmetry, the baryon to photon asymmetry, which is a small number, as we know. It's order 10 to the minus 9. And if you were to ask from observations of metallicity, low metallicity clouds, the abundance of helium, deuterium, and helium-3, what would the baryon to photon ratio be? You get a number that's very consistent with the prediction from the CMB. And so this makes us think we understand what's going on. So BBN can be used to, look constraints for new physics. So I want to come back to isospin breaking in this question. We know the initial conditions are set by the neutron proton mass splitting. The time at which we break the deuterium bottleneck is set by the deuterium binding energy. And then the neutron lifetime is another quantity that comes in. So these will all be sensitive to isospin breaking. At leading order, the deuterium doesn't get a correction from isospin. You need isospin breaking squared. And so then if I focus on the two quantities left, I have the lifetime and the proton neutron mass splitting. And so then the initial conditions are set by the mass splitting. And then the lifetime, here, this is a formula you can pull out of Griffiths. If you have the muon decay, you can calculate this formula exactly. And this phase space factor is an integral you can do exactly. And here A is the neutron proton splitting over the electron mass. What you see is this expression is very sensitive to the neutron proton mass splitting. So if I make a 10% change in the neutron proton mass splitting, I get 100% change in the lifetime. So of course, this puts high constraints on the neutron proton mass splitting. And in the standard model, we know there's two sources of isospin breaking. There's the quark mass operator and the electric charge operator. I'm just ignoring the Z boson effects. And so leading order and isospin breaking, I can split the neutron proton mass splitting into a component from electromagnetism and a component from the down quark up quark mass splitting. So as you know, the QED self-energy correction of the nucleon will have an operator proportional to the quark mass, but there's arguments you can make that that's really second order isospin breaking, numerically at second order isospin breaking. So we're going to ignore that. And then what's new is with Lattice QCD, you can actually determine these coefficients. So I have some number times the alpha fine structure constant plus another number times the down quark up quark mass splitting. And so this number is coming out of a Lattice QCD average. At the time I did this, there wasn't a precise determination of the QED correction. So what I did is I took the experimental number, subtracted the Lattice QCD determination from the strong contribution, and produced a correlated determination of coefficient in front of the fine structure constant. And then what you do, you go look at BBN. What I want to do is now look at, I normalize the code to reproduce known BBN. And what I want to do is study what changes as I change alpha fine structure or the quark mass splitting. And so in order to quantify this, what I'm going to do is I'm going to look at the predicted hydrogen fraction minus the measured fraction divided by the uncertainty on the hydrogen fraction of the early universe. And I'm going to parameterize this as a function of delta over delta physical. So here, if I plug in the numbers, the strong contribution to the neutron proton mass splitting is 2.39 MeV, and the QED correction is minus 1.1, because QED makes the proton heavier and strong isospin breaking makes the neutron heavier. And what's cool, probably most of you already know this, this helium-4, sorry, this is helium-4, not hydrogen. The helium-4 mass fraction basically tracks the neutron proton mass splitting. So if you were to change alpha fine structure and MD minus MU such that you held the neutron proton mass splitting the same, you actually couldn't tell from looking at the helium-4 abundance what universe you're living in. But also, as you know, deuterium is another thing you can look at. And deuterium has a different sensitivity to these two ways of doing isospin breaking. And so here we looked at, this is with Projwal Banerjee, and at the time a student at William and Mary, Matt I can't see his name, Matt Heffernan. Yeah, good. And so then if you combine these two, of course, and do a global average, what you see is because they're orthogonal sensitivity, you get this very tight constraint on the possible variation of the electromagnetic coupling and the down quark up quark mass splitting. And to my knowledge, this is the first result that was able to do a quantitative variation with both the fine structure constant and the down quark up quark mass splitting, because this is the first time Lattice QCD had produced a sensitivity to the down quark up quark mass splitting in the neutron proton mass. So this is kind of neat. So here we see we can only move about 0.5%. So these are 1 sigma bands measured by the observed uncertainties of these abundances in the early universe. And then just for fun, you could see how dramatically different the universe would look like if you were to take larger variations of the couplings. And so here we can see helium-4, you can run up to 40% or down to just a few percent and produce universes that look very different from the one we're in. And what I'm hoping is, as Lattice QCD develops, this is just the beginning of how we can actually quantitatively contribute to understanding of BBN, solar fusion. I happen to be at the solar fusion workshop right now. So here's my conclusion. I'll just leave it up there. I think we're starting to hit an exciting time in that Lattice QCD is now delivering precise measurement or predictions of single nucleon quantities. And in the next 5 years, we're going to start to see much more interesting things like resonant production, pion production, 2 nucleon matrix elements, hypernuclear interactions, so on and so forth. So thank you. Hopefully I've left at least 9 minutes for questions. I'll go find a picture to answer Evan's question while others think about asking questions.
Great. Thanks, André, for this very nice and comprehensive talk. Yeah, so there's one question left in the chat from Evan. I think although Vincenzo replied.
My answer is not going to be my answer is going to be to show you how irrelevant so far Lattice QCD is.
Okay.
This is just kind of funny. I just have to find it.
Yeah.
It looks like Vincenzo responded to it. I mean, I was aware that the bottle result was kind of like, had a global preference, but I was just curious how the Lattice result compared to those two. I mean, André showed the calculations with the uncertainties, but I couldn't translate that into the actual numbers for tau sub n.
Yeah, here you go. My screen sharing is paused. Why? It won't. It's telling me okay, let's try this again. All right, sorry. It's just taking me a second. Oh, my whole. Oh, here we go. Now we'll get this right, I think. All right. So, green line is this is not the latest prediction of BBN. This was something we did a few years ago, so ignore the discrepancy.
We still don't see it. We still don't see the plot.
Yeah,
Sorry.
we still see the slides.
Yeah, it says, what did this get us?
So what is what?
Yeah, the title of the slide said, what did this get us? And then you had some allocation statistics for the different machines.
So what's very confusing to me is I open my talk, it's in full screen mode. I get out of full screen mode. I'm on the same slide as Zoom. I'm just going to share my whole screen. That'll be easier. Here we go. That's the answer. Now
we see a green line.
So ignore the giant pink band. That was supposed to be how irrelevant we are. This is the bottle experiment and the beam experiment. And ignore the discrepancy between the green line and the bottle experiment because I haven't calibrated it against, the best BBM predictions. This is on my laptop.
No problem.
The point was, once I put in the uncertainty on GA, that's the pink band. So we're not at the point where we can even give you estimate. But if we reduce this uncertainty by a factor of 2, and we happen to sit on one or other side of the beam or the bottle, then we could provide some discriminating tension. But yeah, we're not there yet.
Okay. No, thanks, Andre. Thanks for answering that.
What computers can go beyond
Yeah.
GPUs? So Lattice QCD calculations proceed in steps, and step 1 requires leadership class computing. There's no way you can do that on parallel distributed, embarrassingly parallel computers like in the cloud. That's where you really need the leadership computing center, because you have to do one calculation on 20% of the whole computer at once. That's the gauge generation step. Once you've generated the QCD configurations, you transition to an embarrassingly parallel problem, because now what I need to do is I need to compute something like 1 million different independent MPI tasks on those set of configurations to produce a correlation function. So if you had some distributed computing network where each computer on its own could handle the computation, then you could do something like Bitcoin mining type of things where you distribute it across the world. Anybody's willing to open their computer up, or the same way SETI works. But that's probably not very reliable. And so you still typically want access to the leadership computing so that you can run the calculation in a reasonable amount of time. In terms of technology, going beyond GPUs, people are looking at, FPGA type computers, the field programmable gate arrays, and they're also looking at silicon wafers, and they're doing all sorts of things. But the exascale era, I guess you all know, is all the exascale machines are GPU accelerated. And I think it is certainly an open question what post exascale computers will look like. And one thing I'm sure of, though, is the Lattice community has always been amongst the first to get their code working on whatever the next generation of hardware is. So we have a colleague, Kate Clark at NVIDIA, who started off in Lattice QCD, and she back in 2010, 2009, she wrote such ridiculously good GPU code, not just for Lattice QCD, that NVIDIA was like, hey, you want a job? And she's like, sure. And then they pay her to keep developing software for us. So it's pretty amazing. In fact, NVIDIA employs 8 people with Lattice QCD expertise who have some fraction of their time still devoted to developing software for NVIDIA GPUs. But I don't have a good answer for post GPU, other than I know people are exploring it. It looks like silicon wafers. I mean, just like GPUs, it will be more and more compute packed on a single node or a single chip. So you start having to worry about memory bandwidth to pass the data around to different parts of the node. That's the big bottleneck for Lattice QCD.
Okay, thanks. I think we have time for one more quick question. So George, I see your hand.
Oh, I answered Richard's question. Sorry, I saw George's hand and I thought that was the question.
No, thanks a lot, Andre. That was a great talk. It's amazing what can be done at this point. So just on the BBN stuff, I mean, it's really intriguing what you show, and we've always worried about QED corrections. One thing one can think about that goes beyond what you did is to recognize that neutron to proton ratio, is really the history of isospin symmetry breaking, as you say, the history of the weak interactions. And so you're not really in equilibrium. I mean, that equilibrium value of neutron to proton ratio, the chemical equilibrium value, is actually broken significantly by a temperature of order a little less than an MeV. So you're going to get in broad brush the same result, but it would be, I'm wondering how much the QED correction runs as the temperature evolves over that, epoch between a few MeV and, 100 keV when the alpha particles form. That might give you another, Evan Groves, of course, is the expert on this, but one thing we've been harping on for a long time is that this is an out of equilibrium process, and you've got to kind of follow all of the weak interactions consistently, which you can do.
So interesting you should bring that. I don't have a good answer to your question. I think this is great, and it'd be fun to keep talking about it, because with Vincenzo, we actually recently uncovered a, let's call it a 2%, order 2% structure correction to the neutron beta decay from QD. And what do I mean by that? What I mean is you do a pion-fold chiral perturbation theory, you calculate the pion loop corrections, and you realize that, in fact, of course, there's low energy constants you don't know, but if you use naive dimensional analysis to estimate them, you end up with a 2% correction for how QED modifies the bare QCD matrix element for GA. And so what we're doing, and so this is relevant if you want to look for right-handed currents. It's not relevant for neutron lifetime and GA measurements, because it enters both those in the exact same way. But we're gearing up to actually do that lattice QCD calculation. And so we could dream, once we get our handle on vacuum, zero temperature, radiative corrections to neutron decay and neutron proton mass splitting, we could certainly think about trying to answer questions about, well, now let me squeeze this in a finite temperature system and see how much is this going to change at all.
No,
Maybe there's a,
it's just the whole point here is that the expansion rate is very, very slow during Big Bang nucleosynthesis. And the reason for that, of course, is that gravitation is weak. And so, you have this long protracted epoch where things are going out of equilibrium. So you may be sensitive in a cumulative history sort of way to relatively small changes in these couplings or in the neutron proton mass difference.
yeah, sorry, if I understand your comment correctly, you're meaning at 100 MeV, the neutron proton mass splitting might be different because the QED coupling is slightly different, and that's going to,
right, 100 MeV is maybe not terribly relevant for BBN, but sort of in the few MeV to a tenth of an MeV range, it certainly is.
I was thinking of the evolution of the isospin asymmetry from 100 MeV down to like the onset of
that might be
BBN.
interesting too. I don't know. And then one kind of picky thing on one of your slides, I think your kind of cartoon on BBN. If you could find that.
Yeah, looking. I have found the start. Yeah,
I can think of all kinds of interesting things to ask you, but we don't have any time here. But yeah, that one. So in the second frame, so what really takes the deuteron out of equilibrium is the neutrons all get sucked into alpha particles. So the arrow should point the other way in that one.
Okay.
it's destruction that reigns at that point, and there's not much destruction, of course, because
okay.
Yeah.
I was thinking, of course, of a time evolution, but you're meaning more like a causal effect. It's these neutrons mean you can't.
No, it's time evolution. So, I mean, the point is that at that time, at 0.1 MeV, essentially all the neutrons go away. They all get sucked into alpha particles. And so the fuel you have, so if you look in the very left-hand picture, proton plus neutron goes to deuteron, suddenly there are no neutrons. So there's no forward, there's not much of a forward flow in that reaction. It's mostly all destruction.
Thank you. That is a point I did not appreciate until now.
Makes no difference, but it's all right.
What's really destroying the deuterium is actually the dp gamma.
That's right.
Reaction to helium-3, not so much the photodissociation. But
so this, you're saying here, this is really, well, which one was it?
Well, no, when you're destroying deuterium, I mean, this is for George's comment, it's
in the second frame there. Yeah.
Yeah, the reaction that's the most relevant is actually dp gamma to helium-3.
dp gamma
to helium-3 plus a gamma.
Gotcha.
And that's getting cut off.
It's not a big deal.
Right. I mean, the temperature is going down, so that gets cut off very rapidly by the Coulomb barrier.
I never took a BBN class, so I just
There
had to
aren't any
wing it.
classes on
Well,
video. It's all right.
There's that summer school next week. So
Yeah, but yeah.
Yeah.
thanks,
That's a good-
Andre.
Thank you.
Thank you so much, Andre.
Yeah. Thanks, André. Thanks for all the questions. So we have advertised the summer school next week as well. Yeah. So if there are no other questions, then yeah, thanks, André. Again, it was a really great talk. And I'll stop the recording now.
Thank you.
Thanks for